right, hello. So I'm Tessa Kelly, and I'm an engineer at Noverdink, which is an ed tech company helping teachers to teach writing. If you'd like to follow along with these slides on your own computer or whatnot, you can go to slides.com/tessak/color-coding-with-elm/live. So I've written Elm at Noverdink for about 3.5 years, but I've only recently gotten really interested in colors beyond the superficial. I started looking into colors and their use on the web because I'm interested in accessibility. How can we as developers make sure that our users can understand and use our content, no matter how their site differs from ours? All right. I maintain a library of helpers called Test9/accessible-HTML that's supposed to help developers, very much including me, to build applications that will be accessible to everybody. One of the topics that I kind of stalled out on when I first started working on the project originally was how to encourage accessible use of color. I hadn't done much work on how to work with colors accessibly, and I didn't know much about colors in general. So pretty much what I knew was that there was this big hole in the project. Then this isn't changing. That's good. There. Okay, maybe? No. Why are they out of sync? Okay. So this past September, I went to Nordic.js and watched a talk on accessible colors that inspired me. Since we're in Norway right now, some people here may already know this, but there are actual legal ramifications here if a website isn't accessible. So getting accessible colors right is vital. And this particular team developed a strategy for programmatically ensuring that the customizable color options that they offered to users would be accessible. The solution described in the talk seemed simple, and it worked. And so I got really interested in colors, and I started reading about color spaces on the web and developing a new Elm library just for working with colors. I ended up feeling really excited about colors in general, and I hope that you will be too at the end of this talk if you're not already. Oh, and we switched. So now you know all about me. Let's see if we can get a basis for what we're even talking about when we talk about colors. For our purposes today, I'm going to stick to a Eurocentric view of colors. Those are the influences that I know how to map from the world of a few centuries ago to computers today. So take that as a warning. This will be a very incomplete, shallow, and limited sketch. The history of dyes, of botany, of textiles, of cultures, traditions. It's all much deeper and richer than a few names. That being said, let's start out with a big name, Newton. So Newton had major contributions in multiple fields, including studies of light and color. Newton used a prism to split white light into a rainbow, showing that white light is comprised of colored light. Newton also published the first color wheel in his treatise, Optics. So this slide shows his color wheel with segments labeled red, orange, yellow, green, blue, indigo, and violet. The letters on the wheel are there to illustrate his idea of color octaves, the idea that colors reoccur the way that notes reoccur, like regularly. In 1717, a man named Leblanc patented a 3-color printing system. I mention this partly because it's a remarkable achievement, and partly because even though both Newton and Leblanc studied color, the context for their studies was very different. So Newton's work dealt with colors through light, like using a prism to get the colors of a rainbow. In contrast, Leblanc dealt with paper and ink, with materials that actually absorb light. So if your elementary school experience was at all like mine, you're probably more familiar with thinking about colors in the context of materials that absorb light, since you probably spent a lot of time with watercolors, like paper and the little things when you're painting, and then someone else mixes the colors, and then you're like, oh, why didn't you use the water? But paint, including watercolors, are in what's called a subtractive color space. So the more kids use the same watercolor kit, the more every single one of those little paint circles trends toward brown and then eventually black. The colors of the paints cancel each other out, and we end up with a classroom that only has access to brown paint. This is in contrast to how rays of light work. So if you picture your class all holding flashlights with colored lights over the bulb, if one child points their flashlight at a white wall, we expect to see the color of the translucent lens projected onto the wall. If the rest of the class were to raise their flashlights to point at the same circle of colored light, then that color would be washed out. All the colors would have added up to white. So inks and paints are in the subtractive color space, and everything working with rays of light are in the additive color space. Since we're working with computer monitors, we're in the additive color space. So Newton has figured out how to split light into component colors. Leblanc has figured out a system for mixing colors in printing. What next? In the 18th and 19th century, many people tried to describe colors' relationships to each other in terms of three-dimensional solids. Spheres, triangles, cones. Lots of people developed theories and mathematical models around color. Work on the perception of color also continued and deepened. A standout work on perception of color was Goethe's 1810 theory of colors. In 1905, Albert Mansell took color theory forward with a new way of modeling color as a three-dimensional solid. His method was more scientifical than mathematical, and his result breaks out of the previous attempts to describe human perception. So, really quick, any guesses about what Mansell realized about human perception of color? So, think of a guess. Got an idea? Yes. Okay, it's irregular. So human color perception doesn't actually map perfectly to a geometric shape like a cube or a sphere. Which is maybe a surprise, maybe not a surprise. No reaction, not cool? Okay. So Mansell's system for describing colors is still in use today. In particular, by soil scientists and breweries to get that perfect yellowy gold color. The system works through matching colors to each other. If you're a soil scientist and you need to be able to record data on soil color, you'll match your soil against the labeled color plate in his book. If you use a Pantone color system, you'll also approach your work through matching colors against each other. If you specify that a graphic is supposed to be printed with a particular Pantone color, your goal, your expectation, is that eyes that see the finished graphic think that it looks like the Pantone color on the sheet. For web developers, though, we can't control the production of a color. We're constrained by the devices of our users. When we're working on our application on our fancy developer laptops, we're often seeing more colors in more detail than our users will. We can't match colors displayed on all of our users' screens to a beautiful swatch in a book. All we can really do is provide a very precise description of the color we want and hope for the best. Which brings us to web color modeling. So in web development, engineers have continued to model color as three-dimensional color solids, just like our friends from the 18th and 19th centuries. When we use RGB colors, our color space is a cube. Varying amounts of red, green, and blue define three axes. For now, let's think of the maximum amount of red, green, and blue as 1. So at point 100, we have a kind of a pure red. At point 010, we have pure green, and at point 001, we have blue. RGB colors are created through light, so they're additive, so they add up to white. This means that at the origin, which isn't visible in this picture, we'll find black. Then the furthest point along the diagonal at 111 is white. Of course, in the implementation of the RGB color space that we're probably most familiar with, the furthest point along the diagonal is actually 255, 255, 255. We can go from the unit cube to the 0 to 255 cube by multiplying each channel value by 255. Essentially, though, whether we worry about the scale or not, we're talking about adding reds, greens, and blues together to describe the color we want. We're actually using an identical system when we work with hex values. The encoding is different. Hex colors are base 16 rather than base 10 and can be stored more compactly than RGB colors, but we're still describing colors as points in a cube. It takes a little bit of math to get us to and from a unit RGB representation to a 0 to 255 representation and to a hex representation. Really, though, it probably shouldn't matter to us as developers what color system we're working with. Once we have a color, we shouldn't have to care about what kind of a description of the color we started with. If we start with a reddish color in RGB and we decide we want to mix that starting color with a dab of a particular blue, we shouldn't be suddenly stalled by math. We shouldn't be needing to multiply and divide by 255 all over the place. Again, what matters is that our colors match what we wanted, not that the way that we've created them or the way that we've described them is identical. This is where things get kind of interesting, since identical colors don't actually always look identical to the viewer. So, remember Goethe. So he investigated color not only from the perspective of objective observable facts about how light functions, but in terms of how people perceive color. Another way to say this is that he treated color not as an inherent property of an object, but as a physiological reaction dependent on lots of factors. So colorblindness is one of these factors. After images are another. The appearance of colors in relation to each other is a third. So here, you can notice the fun effects produced by layering the blue and yellow lattices. There are two identical pink circles on two different colored backgrounds. So there's a yellow background and a blue background. We slide the blue background, or we slide the blue lattice over the yellow background and the yellow lattice over the blue background. You'll notice that the result is that one of the circles looks kind of purple and one of the circles looks kind of orange. The actual pink hasn't changed. So this effect demonstrates that when working with color, we can't think about a single color at a time. Perception of the color will change drastically depending on how it is positioned and with what other colors. Even though there's no actual blending or anything else, this is just a visual effect. One of the tools that folks often use to describe colors' relationships to each other is the color wheel. Notice that the yellow and blue that we were using are opposite each other on this wheel. If we pick two colors opposite each other, another two colors, we can observe a similar effect. If we choose a green, for instance, whose opposite is pink, notice how our still the same pink circles change. One circle looks extremely vivid pink, and the other circle looks kind of sickly. But how can we actually talk about the color wheel at all, when all we've seen so far is a cube? I've been throwing around this idea of opposite colors, like we have any idea where they come from or how to get them when we've been working with an RGB cube. So this chart shows hues along the x-axis, and then plots 3 lines showing the component red, green, and blue values for each hue. So if you wanted to make a rainbow, like the one at the bottom, using RGB values, you'd probably end up needing to write a function that does what these piecewise functions are doing, which sounds not super hard, but maybe more hard than it needs to be. The color system that you use can have a really big impact on how easy it is to do the operation that you're interested in. If you want to make a rainbow, RGB is probably not the right choice. There are other color systems that make working with the color wheel and rainbow orderings of colors really easy. To make this chart, I used the HSL color space to rotate around the color wheel, resulting in a rainbow, and then mapped over the list of rainbow values to get the component parts, the component red, green, and blue values. And then I used Theresa Sicol's line charts library, which is awesome, thoroughly recommend. Making this chart would have been much harder if I had limited myself to only using RGB color modeling, or if Theresa hadn't made this awesome project. So how does the HSL color space actually work? HSL stands for hue, saturation, and lightness. This color space is a cylinder rather than a cube. So if we take a slice from the center of the cylinder so that we're looking at a circle, we'll see what looks kind of suspiciously like a color wheel. How bright the colors look will depend on how high up in the cylinder we took our slice. If we slice from near the top of the cylinder, the wheel will look washed out. If we slice from the very bottom, the entire wheel will be black. Also, if we're looking at our slice as we move toward the center, all of the colors will trend towards gray. So this image can be thought of, this colored donut, can be thought of as the outer edge of a horizontal slice from about halfway up the HSL cylinder. And then this outer edge has been stretched a little bit to make seeing the hues a little bit easier and to mimic a color wheel. Talking about the hues we care about in relation to each other gives us some great options. We can talk about complementary colors, colors that are opposite each other. if we can talk about triadic color relationships or tetradic color relationships, we suddenly have the opportunity to talk about how colors relate to each other in terms of the structure that we already know well, the rainbow, rather than needing to talk about the constituent parts of each color, like the exact amount of redness in the purple that you're interested in. The HSL color space also makes it easy to adjust the saturation and lightness of a color, which makes it really easy to produce monochromatic palettes like these. So not only does the HSL color space make it easier to understand various hues' relationships to each other, but also to understand what colors are available when you're starting from a particular hue. Okay, so what we've discussed so far. Historical modeling, Newton, Goethe, history. Color modeling on the web, we talked about RGB, hex, and HSL color spaces. We also talked a little bit about color perception and getting our colors to our users. Notably missing so far, Elm. Okay, so let's get into some colorful Elm packages. So I started programming in Elm in 2015 on the 0.16 version. At the time, there was a core color library. This color library was removed from core in August of 2018 with the release of 0.19. There's a lot of numbers in that sentence. So this library supported creating colors from RGB, RGB with transparency, HSL, HSL with transparency, helpers for all of that. There was a helper for converting to grayscale and for generating a complementary color. The library also allowed the developer to extract details about the color, like the component values, and provided helpers for working with gradients. It also offered the Tango palette, which is a palette created specifically for use in software. It is a pretty nice looking palette as these things go. Okay, but as I mentioned, 0.19 removed the color library from core. Some folks still wanted a central color implementation though, and forked the color work. So this resulted in avh4/elm-color. So API-wise, this project is currently fairly similar to the original core version with some additions, like these nice helpers for new ways to build colors. And I particularly like that RGB 255 says what kind of values it expects in the name. That's lovely. And it also has a convenience helper for getting out a color string that's appropriate for use in a style sheet. So a string that looks like RGBA with parens and values. If you were using the core color version before 0.19 and your needs haven't changed, this is probably the package that you want to be using. The project is still under development and it's really community-minded. So if you have thoughts on colors or want to explore ideas on colors with people, this is probably one of the best projects that you can get involved in. There are also 2 major UI projects in the Elm community that have implemented their own color types. So Richard Feldman's Elm CSS project models color in RGB internally, and then externally, Elm CSS provides an API for creating colors from RGB, hex, and HSL values. Similarly, Matt Griffith's library Elm UI models color internally as RGB values, and it allows users to construct colors from RGB component values. Didn't change that fast enough. It also allows deconstruction of the color into component channels. So all 3 of these discrete color implementations allow the user to create colors and use the colors as part of a web application in some way, whether that's through generating a string for use in a style sheet, or managing style sheets and styles generally, or managing HTML and CSS entirely. So what more is there? What more could you possibly want to do with colors? You could play with contrast, explore contrast, talk about accessibility. You could blend colors, mix colors together. You could go from one color and adjust it a little bit to get another kind of color. You could play with generating colors. And then there's also palettes, which we haven't discussed really apart from the existence of the Tango palette. So, starting out with luminance and contrast. So here we have some code. This is an Elm implementation of the relative luminance calculation. So relative luminance refers to the perceived brightness of a color. So you notice on the final line that we're multiplying each channel value, each RGB channel value, by a different constant. The red value is multiplied by 0.2126, the green value by 0.7152, and the blue value by 0.0722. So this is because, generally speaking, people don't see blue colors as very bright. Blues tend to be like very mellow, versus greens and yellows and colors like that, which are very like intense. So we're weighting the channel values in order to take a stab at like how bright a color will seem. The difference in perceived brightness between these different channel values probably relates to the proportion of cones in the human eye that perceive yellows and greens versus reds and blues. Remember, though, that we can only use this calculation to make an educated guess at what the user's perception of the brightness might be. We don't know what monitor or monitor settings are in use, and we don't know that our users' eyes have the average proportion of cones. In fact, we can be pretty much positive that some of our users don't have the average proportion of cones in their eyes. I think the proportion of like cones that users have is probably like 0. How many cones? Like, whatever. What we're working with here is a mathematical model of color that is close enough to reality to be useful. What we're not working with is an objective measure of brightness. But this calculation for luminance is standard in the industry, and it's the one that we should stick to. What I'm interested in as a thought experiment is there a new revolutionary idea about how to think about relative luminance just around the corner? Is there a new way of thinking about brightness? The calculation for contrast relies on the relative luminances of two colors. The contrast is essentially the ratio between the two luminances. Treating contrast as a ratio flattens out fairly complex color relationships. If you talk to an artist or a designer about contrast, they'll probably have a list of various kinds of color contrast that they can share with you. We know as developers that we want accessible sites, and we know that having high enough contrast for text to be legible is part of meeting accessibility standards. But some high contrast text can be hard to read too. It seems to almost like vibrate on the page. Consider this example. The contrast is sufficient, given the right font size and font weight, to meet AA standards for contrast. But it's kind of hard to imagine actually reading an article using this color scheme. Using the contrast algorithm can be a helpful tool for verifying instincts, but there remains more to the interaction of these colors than simply the ratio of the relative luminances. That being said, even though there's more to readable, accessible content than contrast alone, double-checking contrast needs to happen. There are 2 Elm libraries that I know of that provide helpers for calculating luminance, contrast, and for checking against these standards. So Noah Z. Gordon /Elm Color Extra, which is forked from Eskimo Blood /Elm Color Extra, and Tessa Palette both have helpers for calculating the contrast and luminance. Additionally, Elm Color Extra has a helper for finding the maximum contrast option from a list of colors, and Tessa Palette has a helper for checking if a color pairing, given some font size and font weight, is sufficient to meet WCAG standards. Okay, on to blending colors. So Elm Color Extra provides many helpers for smushing colors together, of which I'm demoing just 2 here, difference and multiply. Elm Color Extra draws inspiration from the blending strategies described in the Mixed Blend Mode CSS draft spec, which is super neat, very extremely neat, but also has limited browser support. Task 9/Palette has just 4 blending helpers currently, each of which operates in the RGB color space per channel. So when might we want to blend colors? So for this presentation, I used color blending to build out these overlapping circles. And it turns out it would have been much easier to use the CSS Mixed Blend Mode property with some SVG circles, which I only realized after I'd already built a bunch of SVG arcs by hand, but you know. I also realized in the process of making these that I didn't yet actually have full support for everything that I wanted. What I wanted to do was to be able to easily add colors as though we were in a subtractive color space. But instead, I had to do math, the one thing I wanted to avoid. But in general, I think thinking about color blending is kind of confusing. And often I prefer to adjust one color value at a time. So maybe decreasing the brightness of a particular color to produce shades, or increasing the brightness to produce tints, or changing the saturation of a particular color to produce tones. Both Color Extra and Palette have a bunch of helpers for adjusting colors one attribute at a time in various ways. I won't go through all the options here, but know that there are a lot of helpers ready and available for you. Color Extra also has a pretty neat interpolation function that allows for linear interpolation between two colors in RGB, HSL, or LAB color spaces. So in this example, the central colors were generated through interpolation. The top central color was interpolated through the RGB color space, while the bottom central color was interpolated through the HSL color space. Looking at this, that looks more red than it does on my screen. It's a gray. It's like the slides are making my point for me. That's not the color I intended. Oh no. Okay. And Tessa 9 palette also includes helpers for generating various palettes based on color wheel or HSL relationships. So we can generate a complementary color, or we can generate two colors that form a triadic relationship, or generate a tetradic scheme. Okay. So an idea I've emphasized today is that colors exist in relation to each other. As we start to think about picking colors that relate to each other, or adjusting colors and generating colors that relate to each other, we move closer to the idea of the palette. We've already seen one palette, the Tango palette, but there are many more palettes in use across the Elm community, and there are definitely some neat opportunities for new palette projects as well. So right now, there's a package specifically for the Color Brewer palettes. These colors are meant for use in maps and like showing data on a map. What you might notice about these is that the color palettes don't have visual hotspots. For most of us, looking at each column, every cell appears approximately visually evenly weighted. Displaying data without color-based hotspots is really vital to communicating clearly about the data. Of course, if your goal with your chart is to manipulate your users into believing something that the underlying data doesn't support, color hotspots. Use those yellows, bright colors. So each of the ways to generate a palette in this color brewer scheme is named after the type of data that the cartographer might be working with. So the palettes are fundamentally about the data that they're meant to show. Another library dealing with showing data effectively is the line charts library, which aims to make good color choices by default. So the line charts library limits the colors that can be used in the produced line charts to a palette of colors that work well together. So here, we have some stacked line charts displaying the area underneath each curve. These three charts use every color available in the line charts library. So I wouldn't say that these particular charts are very effective at communicating information, since the axes are X values and Y values, and it's not real data, but I think that they look pretty nice. All the colors look pretty good together, and they're hotspot free. Visually, it's pretty easy to parse. As an example, in the other direction, X11 colors definitely don't all look good together. The goal of this particular palette, though, was not to produce a set of colors that developers could simply slot together to produce beautiful results, but to create a set of colors that user agents could consistently display. And now we come to one of my favorite palette generation strategies, Cubehelix. So Professor Dave Green developed the Cubehelix color palette generation scheme for use in astronomical charts. His goal was to produce a scheme in which none of the colors popped, an algorithm for creating even intensity colors. The cube in the name Cubehelix refers to the RGB color cube. The helix, from the name Cubehelix, is a helix that goes around the diagonal drawn from black to white through the cube. So from the back that you can't see through to that point that's white. Suppose we generate 256 colors using the Cubehelix palette. Rather than varying linearly, the intensity of the red, green, and blue components will vary. This makes for a much more even-looking palette that is also customizable. The Cubehelix palette is generative, which means that we can adjust the configuration we pass in to produce a palette that meets our needs. In this second example, that I haven't changed yet, I've changed the number of rotations, and I've also changed the gamma factor. And this pulls our result away from the diagonal, but still creates a set of colors that is pretty even, visually speaking, and looks pretty nice. And there's a ton more that you can do with the Cubehelix configuration, and it's definitely fun to play with. Okay, so there are many more neat palettes and neat color tools in existence, and there's definitely room to bring more of it into Elm. There are also a couple of projects that I didn't mention, including a library of colors aimed specifically at use in material design projects, Elm Material Color. There's also a color picker for if your user agent isn't going to be able to support the HTML input color selector. And of course, apologies if I should have mentioned your package or project and I didn't. My hope is that at this point, you are interested and excited about colors, and I hope that you learned something. If you're interested in exploring some not quite polished code that I used to make the examples in this presentation, let me know. And just as a thing to think about, I hope that we can take a moment to consider our relationship to colors. I hope that we can pause and think about folks with different sight than our own. And I hope that we can pause and think about folks whose perspective on colors in general is different than our own. Maybe we can learn to appreciate an approach to color that we haven't seen before. I think that we should also consider what we want our relationship to colors to be. Are colors on the web really more interesting than a point on the RGB cube? Is there value that we want to exploit in standardizing around a library? Is there value in implementing to and from RGB helpers per project? Are colors actually core to what we as web developers do? What can we do that would make meeting varied user needs easier? For me personally, as I continue to work on my palette project, I plan to consider all of these questions. I hope you'll join me in thinking about them, and I hope that you'll join me in being excited about the colorful future of Elm and the colorful future of the web. So thank you very much.